So say we got a particle travelling round and round a circle. Let's say that it travels like we normally have the angle moving around the circle, anti-clockwise. Let's say it starts here and the particle just travels round and round and round the circle at a constant speed as it goes round the circle. Imagine if you're looking at it from above. You're looking straight down and watching what happens. All you see is it go backwards and forwards. If you're looking down, you just see it go backwards and forwards. It starts here and it goes along there and back and along there and back and along there and back. That's all you see if you're a great height up and you're looking down. In fact, this black curve here describes the motion relative to the angle. As you spin around, it describes what's happening just as a horizontal situation. It's out at 1 and it ends up at 0, and then it goes to -1, and then it comes back to 0, and then it goes to 1, and then it goes back again. And it goes backwards and forwards and backwards and forwards between 1 and -1, over and over and over. But the interesting thing is, if you think about it, when you're looking at it from above, even though it's going round and round the circle at a constant speed, going horizontally, backwards and forwards, that won't be a constant speed. It'll take ages to move along this bit, because it's kind of going up, and then it'll move fast through this bit. There's a lot of horizontal cranking here. And then it'll take ages, because there's a lot of vertical happening here, to move this last bit. So it's going to move slower, but it's going to speed up and be at its maximum moving through here, then slow down until it gets to the end and stops and turns around, and it starts picking up speed until it's at its maximum speed, and then it slows down and it stops. Now we know that this is y equals cos theta. What is the derivative of cos theta? You know, if we had the distance, the displacement, location mapped out using that black wave, if we differentiated with respect to time, we could actually get ourselves the velocity of what's going on. So what's the derivative of cos? Sine minus sine. Very good. So if I do a picture of not sine while this is going on, but minus sine, I just need to flip what I've already got drawn there. Okay. Flipping what I've drawn as the green sine wave, it's actually the flip of it, because the derivative of cos is minus sine. So this blue one here is minus of what's going on vertically, but it's the minus sine. That would represent the velocity as such. When is the velocity then at its maximum? Yeah. The velocity gets to in this situation, and that is when the location is at 0, and this is at 3 pi on 2. Let's think about that. Spin around to 90, 180, 3 pi on 2, and we're talking about horizontally. The particle's just moving backwards and forwards horizontally. It starts here when the angle is 0, and it moves along this way as the particle goes around. There's the angle of 90, and it keeps going, and there's an angle of 180, and then it comes back, and there's an angle of 3 pi on 2, or 270, and that's when the velocity is at its maximum. Well, this is also maximum, but maximum negativeness, because if that way is positive, then that way is negative. So it's actually going just as fast, but in the opposite direction when it first goes through here, right? At pi on 2, it's at its maximum, but maximum in that direction. So as the particle moves up here, it's going at its maximum horizontal, and it's going at its maximum horizontal, and then here it gets to 0, turns around, and it's going at its maximum horizontal there, but in the positive direction. So it's going fastest as it goes through the middle, and it hits 0 in terms of its speed when its location is here, 0 speed, location at pi, or 180, 0 speed, location at 2 pi. Location's black, speed is blue. So it's not moving at all here, velocity-wise, it's 0, starts picking up speed, going really fast, slowing down, and stops. Starts picking up speed, goes really fast, slows down, and stops from a horizontal point of view. You could examine it from a vertical point of view as well. If you were looking at it from the left, then you get the green curve that we had, the sine curve. You get this one here as its position or displacement. So it would, if you're looking at from the left, if it starts here, it starts at 0, right? And then as it goes around, it comes up and goes down, and then it comes up and then goes down. If you only care about that, then it's going to be at its fastest when it's moving through here like this, and at its slowest when it gets here and stops. Then it turns around, takes a while, but it's picking up speed and it's going fast, and then it slows down. Remember, the particle always goes at a constant speed as it goes around the circle, but if you look at it just from a horizontal or a vertical perspective, then you've got something that's oscillating in a line, and at its extremities, it's got to stop and turn around, so it's at its minimum speed, and at its middle, it's going at its fastest. And it just depends which side you decide to call, which direction you decide to call positive or negative, as to whether you'd say which way is the maximum or minimum. But if we look at this one, if it unfolds like this, starting at 0 and moving around, then vertically we go up and down like that, we would get y equals sine theta representing that, or y equals sine t, if you want t to be the function of, if you want this to be a function of time. And if that's the case, what's the derivative of sine theta? You're right, cos theta, just straight cos, you don't have to do a negative this time. So the black curve that we've drawn represents the velocity now if we're looking from this side and only worrying about it starting here and going up and down and up and down. Starting here and going up and down and up and down and up and down to represent the constant motion around the circle. So it's saying when it starts, it's at its maximum velocity already. If you're looking at it from this point of view, the green one, it's at its maximum velocity. And after pi on 2, the black is at 0, which is the velocity for the green position. And that makes sense because it starts here, right? And it goes up here and it stops at pi on 2, turns around, and it's going fast through here, just negative, right? So it's at its maximum but negative as it comes back through here at 3 pi on 2. So you can describe motion horizontally or vertically of this particle that's travelling around at a constant speed. You can describe it by a wave, depending on which one you want to use, but it's a cyclical wave, and therefore you're going to call it harmonic motion, and we call it simple harmonic motion.